In the next section, we'll put all of this together, and it will both be required in a way using this this new technique that you haven't seen. So that's another tiny little gem maybe that you enjoy. The exhaustive tabulation technique is sometimes called the 4 Russians trick, and you find this in the literature many times. It's a terrible name. For one, it's super derogatory. Also, I think it's only for two, I'm sure they're Russian, but the others, it was just the Soviet Union at the time, and authors in the US didn't care too much. So just as a kind of, you need to recognize the term 4 Russians trick because it's in wide use. I don't think it's a good name. So exhaustive tabulation is a much more telling name. That's pretty much what it is about. But yeah, it may be reasonable to attribute the 4 authors that first invented this technique. But what is it really about? We'll first use a trick we've seen before. We have a solution for the arrangement problem with n log n preprocessing time and space, but constant query time, which is close, but not quite what we want. But as I said earlier, if we just reduce the input a slight bit by a log n factor, then m log m turns into O of n, just by the cancellation of this log term. But how can we make use of that? One way to do that here is to break the array into regular-sized blocks of roughly log n elements each. For what's on this slide, this curious factor of 1/4 doesn't matter, but it will matter later. So let's keep that in mind, but I'll just stick for this slide with roughly log n numbers in each block. And then instead of remembering all the elements, we'll just keep the smallest of each block in this blue array. And I think my drawing is roughly to scale. So this log n factors doesn't sound like such a lot, but it's reducing it quite a bit. So you keep just the minima of each block. And on this much smaller array, we can use our n log n solution from before, the sparse tables. So in a way, we can solve RMQ queries on block level. If you just care about queries that contain entire blocks, so a query like from here to here, you can basically solve that with just looking at the blue thing, because the answer will be one of the blue block minima. But of course, that's not all. We can have queries that straddle blocks or cut a block in half or between 2 arbitrary positions. So that's not good enough, but it's at least a partial solution. In the general case, we can at least decompose a query into different parts now. So a general query from I to j may look like the red one here. And then there's a green part, which is the remainder of one block that still is in the query part, but it's not an entire block. And you can have the same thing at the end, a prefix of a block. And then there may be a middle part that spans entire blocks. For the middle part, we can use the trick from the previous slide. We just store the minima of each block. And I lied a little bit on the previous slide. We store 2 arrays because we need the minima and we need where in the block is that minimum. We need both pieces of information to solve the puzzle, but it's just a factor of 2 in the space if you want. So here, this B array stores the relative index within the block of the minimum. So this is 1 because this is at position 1. This is 4 because it's at position 0, 1, 2, 3, 4, and so on. Okay. So with that, we can decompose the arrangement query into different parts. And again, we're using the same trick all over as we did before. The minimum in the red range, it has to come from somewhere. It can be in the blue part, or it can be in the left or right green part. And we still have to figure out which of the three it is. But we can reduce the candidates to these three options. So this set K is a set of positions where could the minimum be, and we can nail it down to one of three positions. So this is constant time to evaluate. And what are the positions? Well, the position 1, the first green one, is wherever is the minimum in this green range. And we don't know how to do that yet, but at least it's local to one block. It's just a tiny range. And the second green block is symmetric. It's the minimum in this prefix of a block. We don't exactly know how to do that, but we'll come to it. And it's local to one block. And the middle part is using the sparse table, referring to the previous slide, because these are covering entire blocks. The minimum must come from one block minimum. And so, well, formally written, we're using RMQ on M, the copied values of the minima. But we also need to access the array B to know at which position is the minimum. So far, so good? So if you understand this slide, you get most of the key idea from this. The rest is a bit technicalities to get it to work. And the formulas are a bit a nuisance, but the picture, I think, conveys the idea without much of the nasty detail. So we have only 3 values to check. 2 are from intra-block queries, local to one block, and 1 inter-block queries. And for the second one, the blue one, we already know how to solve it. See the previous slide. We just use sparse tables. So the only thing we have to still worry about is how to find range minima if they're in a tiny range within one of these blocks. So that's the green bit. And we would like to do this with linear space and pre-processing time over all the blocks, because otherwise we don't get our ultimate solution, linear pre-processing time in space and constant query time. So we have to somehow do this pre-processing of all these blocks. So the number of blocks is denoted by m as before, and that's n divided this small b, and that was essentially n divided log n blocks. The trick why this is at all possible is that each of these blocks is really short, namely roughly so many numbers. If we build a Cartesian tree for each of the little blocks, there's only so many ways that this Cartesian tree can look like. Just because we reduced it to such a tiny range that all the different options condense to 1 out of the Cartesian trees for b elements, and we know there's at most 2 to the 2b such Cartesian trees. That's what we used our little tricky tree encoding for. So each of these Cartesian trees can be encoded with 2 times b bits. And that's, if you just work out the math, is a half log n. Now, why is that helpful? The reason is that if you take 2 to the power of 1/2 log n, that's just square root of n. And that's not a big number. So you can afford to just store all possible shapes of Cartesian trees for these tiny blocks, and have one big table where you write down all solutions. So in a way, we're doing the pre-compute all solutions for each of the possible ways that the blocks could look like. And the trick, the magic that makes this work is there's square root n different types of blocks, how they can look like locally, but many more blocks. So we will have a lot of blocks that look exactly the same through the range min lens. Many equivalent blocks. And that's where the exhaustive tabulation technique comes in. it consists of these 3 steps. We replace each local block, so the little block of numbers, by the code for its Cartesian tree, so by 2b bits each. Then we have a table separate from that that lists all possible Cartesian trees and all the arrangement queries in these Cartesian trees. We can afford to be generous there because there's only root n of them. It's a lower order term. And then we use the type of a block as the index in a large lookup table. For that, let me show you this this example before we come to this. So the way you should think about this large lookup table is the following. For each Cartesian tree shape, say B is 4, to have small examples. What can a binary tree over 4 nodes look like? It could be like this, or it could be the other way around. That's sorted lists. But of course, there's many other options. Let me pick a less degenerate one. Oh, come on. So I have 1 row in this table for each shape of the Cartesian tree and each position I and each position j. For example, one entry here could be for this tree and these 2 indices, that's these 2 nodes, the range minimum, the lowest common ancestor is 1. So I would have this entry. But I would have another one with the same tree, and the whole range would also be a 1. And another one, 0, 1, and that would be, again, the 1, well, because that's the root. So you can imagine how this looks like. For every possible tree shape and every combination of I and j, you have a row. But because the number of possible tree shapes is small enough, we can do that. What we also need is for each of the blocks that our array has, we compute the little 2b bit representation of its Cartesian tree. And so instead of storing this tree here, what we really store is its encoding. So that's 0, 0, 0, 1, 0, 0. In this case, you can check that. And so you will arrange this table so that these codes are in order. So this is really the index in the table. If you know the tree encoding, you can jump to the right position in the table with just looking up the position in an array. All right. Here's the math of how big the table is. We have square root n block types. We have b squared combinations for I and j. So that's square root n log squared n rows, but that's much, much less than n. And we can compute them quickly. So the overall preprocessing time for the table is still linear. And if you put all of that together, we get our linear preprocessing time, constant query time solution. So again, this was all about solving the little green parts, for which you would use the query for the green part would look up the code for this little block, use that as an index into the rows table, and then use the positions I and j to look up what the arrangement in that little block is. All right, that gives us, by what many slides ago was stated, we have a solution for arrangement. We get the same with a plus or order n on the pre-processing, but that vanishes here. So we get the same time for LCEs, lowest common and longest common extensions in strings. And that was the black box from Unit 6. The pre-processing and query time in this case are best possible. You can, at least in this combination, you can't get faster queries than than this. And if you want something with fast queries, you need to read the array at least once. It's admittedly more complicated than some other things we've seen, but it's still a somewhat practical solution. You can implement this with these lookup tables. If you choose the parameters right, it can work fast in practice. And I want to point out that this is also closer to actual research. So the solution I presented is also from this millennium. It's not so long ago that people thought about this. And you can think about how to further reduce the space you use. And you can even play the game a little differently. Our solution still needed the array at query time to compare a few things. We could narrow down the minimum to 3 candidates, but we still had to do comparisons to find out which is the actual minimum. But you can avoid that if you go to the Cartesian tree right away. So then you can give me the array for pre-processing time and then take it away from me. You don't need it at query time anymore.